Hello viewers, Ronald taking you through the story for A-level pure mathematics, and this video I'm going to go through the topic of hyperbola, which is under conic section. So this video is suitable for students in both senior 5 and senior 6 offering principal mathematics as part of their combination. So before we start, let's look at the course outline. So math paper 1 is divided into 5 parts. The first part is algebra, where 2 questions come in section A and 2 in section B, and these are the topics. Then trigonometry, where 1 comes in section A, 1 in section B, and these are the topics. Then geometry, where 1 comes in section A, 1 in section B, and these are the topics. Then vectors, where 1 comes in section A, 1 in section B, these are the topics. Then calculus, where 3 come in section A, 3 in section B, and these are the topics. So what is ticked means that it has already been covered. So if you want any, what you need to know is the part where it belongs. For example, if it lies in calculus, at the end of the video you'll see an end screen in this form. So just double click on this folder of calculus and it will take you to all these videos. If it's in vectors, you double click on vectors. If it is geometry, you still double click on geometry, and so on. So just now start on hyperbola. So like we said under the video of parabola, you remember we said that eccentricity, when the eccentricity is greater than 1, it becomes a hyperbola. And the good thing in your mathematical logbook, there are some parameters which we need on this video of hyperbola. So we need the general equation of a hyperbola, which is this. It is a minus. It's a little different from the ellipse. Ellipse it was plus, but now it is minus. Then the general point is here. Here instead of cos we use sec, instead of sine we use tan. Then the eccentricity, this is greater than 1, here it was less than 1. Then the b squared, here it was 1 minus e squared, here it is e squared minus 1. So you need to know those differences. But the good thing, they allow you to go with your mathematical logbooks, so you can easily get them from your mathematical logbook. Then the foci, it has the same formula. Directrix also same formula. So first we need to know how a hyperbola, we need to know the shape of a hyperbola. So we shall draw the axes, label them, then we shall draw the directrices. This is x equal to a over e, and also x equal to negative a over e. Those will be the two directrices. Then we have what we call the asymptotes. I think remember that under curve sketching for rational functions in calculus. So those will be the asymptotes where the curve never touches. Then you shall draw the curve. It's in that part with this is the focus. There are 2 foci, so there is also negative 1. So you shall draw that curve on the side, and this will be the negative foci. So this is how a hyperbola looks like. Remember, it never touches these asymptotes. So we shall now derive the equation of a hyperbola, which we saw in our mathematical logbook. So we shall consider the variable point which moves along this hyperbola. So now we shall try to derive the equation of the hyperbola. So we shall start from eccentricity. I think remember the definition is PS over PB. Then when I cross multiply, I come up with that. Then this PB is the distance between P and B. Distance between 2 points is given by that. Then also distance between points P and S is given by that. So when I square both sides, I'll come up with that. The whole of this is 0, so it cancels out. Then when I try to expand this bracket, I'll come up with this. Expand this, I'll come up with that. So when I open this bracket further, this is e squared and this is e squared, so they cancel, you remain with just a squared. Then here there is e squared over e, so 1e cancels, remain with 1e. That's why you see here 2aex. Then here the whole of this e squared multiplies with this to give you that. So simplifying gives you that, and collecting like terms give you that. Now I'm going to divide throughout by e squared minus 1 to give you this step. Then when I cancel out this and this cancels, this and this cancels, and this and this cancels, remain with 1 here. Here remain with only x squared over a squared, and here remain with the whole of it. So I'm going to replace the whole of this with b squared to become this, and that will be the equation of the hyperbola. So they cannot tell you to derive it, but we only need to know how it comes about. So now shall go to the asymptotes of the hyperbola. So we saw that a hyperbola has two asymptotes. Now we need to go to know the equation of those asymptotes, since they are not given in your mathematical logbook. So we shall come and say that from this equation of the hyperbola, we shall try to make y squared the subject. I'll come up with this. Then from here, I'm going to factorize out this x squared over a squared. It will come out to give you this, and here it will now be 1. Then here it will be the reciprocal of this, which is here. Now putting square root on both sides gives you plus or minus. Here, don't forget this plus or minus. Now shall come and say that as x tends to infinity, the whole of this, because 1 over infinity is 0, so that is why the whole of this tends to 0. And because it tends to 0, it means that we shall only be left with this, because this will be 1 minus 0. Square root of 1 is always 1, so you only remain with that. And those will be the equations of the asymptotes. So the equation of the asymptotes are always in this form, bx over a. So when you have the value of b and the value of a, you can easily state the equation of the asymptote, as we shall see in the questions. So in summary, this is what we have. The equation of the hyperbola is this eccentricity is given by that. It's got by making e the subject in this expression of b squared equal to a squared, or in brackets e squared minus 1. So when you make e the subject, you will come up with this equation of the eccentricity. Then foci is that points these ones, that's be plus or minus. Directrices are in this form, and asymptotes are these ones. Now these asymptotes are not available in your mathematical logbook, so you have to just remember it that's bx over a, but it has to be plus or minus. Then we shall go to general point on a hyperbola. We already saw it, now let's see how it comes about. So we shall say that comparing the equation of the hyperbola this with the trigonometrical identity of this, I think remember this under trig identities, we shall compare and say this one is equal to this, and therefore we shall come up with x being equal to a sec x when you put square root on both sides. Then also the whole of this will be equal to this, therefore y is equal to b tan theta. Therefore the general point on the hyperbola is given by a sec theta, b tan theta. The good thing, this general point is also available in your mathematical logbook. Now this theta is what we call the eccentricity angle. So now we shall go to condition for tangency. So here we want to prove that a given line is a tangent to a given parabola. So consider a straight line y equal to mx plus c and a hyperbola this. Substituting for y into the equation of the hyperbola will give us that expression. So where there was y, we put there mx plus c. So when I get the LCM, multiply throughout by the LCM, I'll come up with this line, and then I'll open this bracket to come up with this. Then I'll try to collect like terms. This one gives you this, then this is that, then these two, when this one comes this side, you'll come up with this expression. Now by comparison with a general quadratic equation, I think by now you know why we use capital letters, because small a is already available in the given expression, and small b is also available, and small c is also available. So we can't use small letters here because they will be colliding with the ones in the given expression. That is why we use capital letters. So shall come as that a is that, b is that, c is that. Note that on b there is a negative, don't forget the negative. Also on c there is a negative, so don't forget them. So you come as that for tangency, the discriminant is always equal to 0. So I come and substitute for b, a, and c to come up with that expression. So what I've done, I've taken the whole of this side. That is why you see an equal sign here. Now open brackets, open this bracket to come up with this. Then here there is this negative, it will come out with this 4 to give you negative 4. There is also this a squared, it will come out to give you this. Then after that we shall write this and also write this. We have just rearranged the given expression. Now next you realize that this 4 is common, and also this a, there is a squared here, it can cancel with one a squared here to remain with only a squared there, and these ones also remain. Then here we shall only remain with this and that. Then now I'm going to open this bracket, but remember I'm maintaining the negative. Then from there I'll put this negative inside to come up with this expression. Then from there I'll come and realize what cancels. So this and this will cancel. I'll remain with 0 here, and here I'll remain with this, as you can see it here. Now from there I realize that b squared also cancels. Here it remains b squared, here it cancels, remain with only negative c squared, and here this one cancels to remain with only a squared, m squared. So when I take this one this side, I'll come up with c squared equal to a squared m squared minus b squared. So it is a little somehow similar to the one we derived under ellipse, only that for ellipse this was a plus, but for a hyperbola it is minus. And now we shall go to tangents and normals to a hyperbola. So given this hyperbola, the equation of the tangent and that of the normal of the hyperbola at a general point, remember this is a general point, can be got as follows. So the first thing to do, we have to get the gradient function by differentiating the given hyperbola. So when I differentiate this, I'll come up with this expression. This gives you that, and this gives you this, and this gives you 0. Then gradient function will be got by making dy dx this subject to come up with this as the gradient function. So at this point it implies that x is this and y is that. Therefore I'm going to substitute for x and y in this gradient function to get the gradient of the tangent. So gradient of the tangent will be got by substituting for x and y to come up with this as the gradient of our tangent. Now I have the gradient and I also have a point on a line, therefore I can easily get the equation of the line, which is the equation of the tangent, which passes through this point and has this gradient. To do that, I'll consider a variable point xy on that line. Therefore changing y will be this and changing x will be this, equal to the gradient. Cross multiplying gives you that. Opening brackets gives you that. So now here what I've done, this one, it is minus. When it goes this side, it's going to become plus. That is why you see this plus. Here, this is already here, and this is now here. What I've done, this sec squared, I've expressed it in terms of tan. Remember, sec squared theta is equal to 1 plus tan squared theta. So when you open this bracket, you'll come up with negative AB minus AB tan squared theta. So this AB tan squared theta will cancel with this to remain with only negative AB. So this tan is the same as sine over cos, and this sec is the same as 1 over cos. So in the end, I'll come up with this as the equation of the tangent to a given parabola. So that's the general equation of the tangent to a given parabola. What about the equation of the normal? We shall remember that the normal and the tangent are perpendicular to each other. What does that mean? It means that the gradient of the normal is equal to the negative reciprocal of the gradient of the tangent. So I'll come up with this as the gradient of the normal. Now, using the general point and the gradient we have got, I can easily get the equation of the normal, still following the same procedure as we did under tangent. So when I cross multiply, I'll come up with this. Open brackets, you'll come up with that. And now from here, what I did, this is minus. When it crosses this side, it becomes plus. That is why you see a squared plus b squared. So both have tan theta sec theta. That's why we pulled it out. Then this sec theta is the same as 1 over cos, and tan is the same as sine over cos. And this is tan, we shall leave it there, but this sec it is 1 over cos. So this cos in the denominator is throughout, so we can cancel it out to remain with that as the general equation of the normal to the hyperbola. So with that, we shall go through some questions. Question 1 came from UNEB 2007. Paper 1, question 11, and says, Roman 1, show that the equation of the tangent to the hyperbola this at point this is given by this. So this is very similar to the one we have just derived. So let's do it sharp and we go to Roman 2. So we shall get the equation of the hyperbola, then differentiate it to get the gradient function. So when I make dy dx, I'll come up with a gradient function. So these are some very steps we have gone through. So at this point, x is this and y is that. So I'll come and substitute to get the gradient of the tangent. So we have got the gradient and also have a point on the hyperbola, or point passing through the tangent. Therefore, we shall use those two to get the equation of the tangent. So change in y over change in x is equal to gradient which we have calculated. Therefore, cross multiply. So these are the same procedure as we did. Open brackets to come up with that. Then take this one this side to come up with that, and this one reduces to that. Then simplify to come up with that. Then change this tan into that and this sec into that, and that will be the equation of the tangent. So next is to express in the form which was given in the question, and that's what they wanted. So now we shall go to Roman 2. Roman 2 says, find the equations of the tangent to this hyperbola at points where theta is 45 degrees and where theta is equal to negative 135 degrees. So that's the given hyperbola. And by comparison with this general equation of the hyperbola, we shall realize that a squared is this and b, therefore a is that. Also b squared is this, implying that b is that. So we take only the positive values in this case. Now the equation of the tangent becomes this. Remember, this one was already got in part A. That is why we just substitute for b and for a. Now at theta equal to 45 degrees, it implies that where there is theta, you'll put there 45 degrees. But 45 is the same as root 2 over 2, so substitute for cos 45 and sin 45. Then multiply through by the LCM to come up with that. Now what about when theta is negative 135 degrees? So where there is 45, we shall replace it with negative 135 degrees to give you that. Now sin negative 135 degrees, negative root 2 over 2, and cos negative 135 degrees is equal to negative root 2 over 2. So simplifying gives you that, then making this one positive, you'll come up with this as the equation of the tangent. So those are the two equations of the tangent. Now part C, they wanted you to get the equations of the asymptotes. So you shall remember the general format of an asymptote is that bx over a. So we come and substitute for b, we solve b as 3, and substitute for a, we solve a as 2, and remember to put this x. Also remember to put the plus or minus to make them two asymptotes. And simply that's what they wanted. So now we shall go to what we call rectangular hyperbola. Now this is a special case of this hyperbola, and it occurs when these ones denominators are the same. So when a is equal to b, it implies that we shall get what we call a rectangular hyperbola. So that means that where there is b, we shall put there a squared to come up with this, and multiplying that by the LCM, you'll come up with this. Now this is difference of two squares. And so that, and furthermore, the asymptotes will be this, because remember asymptote was b over a. Now b over a is the same as a over a, which is 1. That is why it is just y equal to plus or minus x, and therefore they are perpendicular to each other. Now from this one, which we already got, there is some difference of two squares, so we shall come and get difference and sum here. Now using the asymptotes as coordinates, remember they are perpendicular, meaning that we can rotate and use them as coordinates. So it implies that this becomes the y-axis and this becomes the x-axis. Therefore we shall now replace with capital letters. Remember in LOCI, capital letter is different from a small letter, so now the whole of this will become the y-axis, so we shall call it capital Y. And this becomes the x-axis, so we shall call it capital X. The equation of the rectangular hyperbola then becomes this, because remember this one is now capital Y and this one is now capital X. But we don't know this C, so this C, we have just replaced this A to become C. And the asymptotes of this rectangular hyperbola are this and this. So now that's when the rectangular hyperbola is in this form, the asymptotes will become x equal to 0 and y equal to 0. But when it is in this form, when written in this form, the asymptotes will become plus y equal to plus or minus x. So always remember that. So it depends on the format in which they write your rectangular hyperbola, but most questions they will write their rectangular hyperbola in this form. Therefore remember that x equal to 0 and y equal to 0 will become your asymptotes. So now the equation of a hyperbola now becomes this and this. So those are the two curves which will represent our rectangular hyperbola, and these axes will become your asymptotes. So the curve must never touch those axes. And when it's in this form, the general point on a rectangular hyperbola will be given by ct as the x-axis and c over t as the y-axis. Now this c is constant, but this t is the one which is variable. It can be p, it can be q, it can be any letter as long as it is variable. But the c is always constant. So let's go to tangents and normals to a rectangular hyperbola. So given a rectangular hyperbola this, the equation of the tangent and that of the normal at this point, remember this is the general point on a rectangular hyperbola, can be got as follows. So shall Still follow the same procedure as we did under hyperbola, only that now here we use this general point and we use this equation. So we shall quote our equation of the rectangular hyperbola, then differentiate it. So when I differentiate, I'll come up with this, and then after that I'll make dy dx the subject, which will become our gradient function. And then I'll remember that at this point x is this and y is that. Therefore, substituting for x and y gives you the gradient of the tangent, which is -1 over t squared. So now we have the general point and also the gradient of the tangent. Therefore, you can easily get the equation of the tangent. So changing y over changing x will be equal to the gradient cross multiply to give you that, open brackets to give you that, then rearrange, and that will be the equation of the tangent. What about the equation of the normal? You shall remember that normal and the tangent are perpendicular to each other. Therefore, gradient of the normal will be -1 over gradient of the tangent, which will be t squared. So now that I have the gradient and I have a general point, I can easily get the equation of the normal. So changing y by changing x equal to gradient cross multiply, open bracket, simplify. So this one, what I've done, I've multiplied throughout by the LCM to come up with this. Simplify to come up with that, and that would be the equation of the normal. So the procedure is always the same as the one for hyperbola, only that here the general point changes. So that we shall go through some of the questions. Question 1 came from UNEB 2016, paper 1, question 14b, and says the normal to a rectangular hyperbola this at a point this meets the asymptotes at m and n. Find the length mn. So you have to draw the sketch. Then draw our rectangular hyperbola is always in that form. The axes are the asymptotes. So at that point there will be a tangent and there will also be a normal. Now they say the asymptotes, this normal means the asymptotes at m and n. So one intercept will be m and another one will be n. So they want the length of mn, they want the distance of mn. So we have to get these 2 points, then we get the distance between them. So for you to do that, you have to get the equation of the normal. So to get the equation of the normal, you have to first get the gradient function. So differentiating gives you that. Then gradient function will be that, get the substitute the given point to get the gradient of the tangent. After that, we remember that gradient of the tangent and that of the normal, their product is equal to -1. Therefore, we shall come here and say that the gradient of the normal is equal to -1 over gradient of the tangent to give you a half. Now I know the gradient and I know a point. Therefore, the equation of the normal will be given by changing y by changing x equal to gradient. Cross multiply to give you that and simplify to get that as the equation of the normal. Now the asymptotes are x equal to 0 and y equal to 0. I think you remember that. Therefore, for the asymptote this, substitute x equal to 0 here to come up with y equal to 3. Therefore, m is 0, 3. What about for the asymptote y equal to 0? Substitute y equal to 0 to come up with x equal to -6. Therefore, n is -6, 0. Now I want the distance between mn, so to be given by that formula, and then we shall come up with this as the required distance. So now we shall go to question 2, which came from UNEB 2006, paper 1, question 4, and says prove that this equation is a tangent to the rectangular hyperbola whose parametric coordinates are this. So x is that, implying that when I make t the subject, it will be that. Then y is given by that. Therefore, when I substitute this t here, I'll come up with that. Therefore, in the end, I'll come up with xy equal to 3 as the Cartesian equation of the rectangular hyperbola. But I already know that equation of the tangent is given by that. Therefore, to prove, I have to substitute for y in the equation of the rectangular hyperbola. This gives me that. So where there is y, I'll come up with a substitute with this. Open brackets, simplify to get the quadratic equation. Now for the line to be a tangent to the given rectangular hyperbola, the discriminant must be equal to 0. So come and substitute for b and c, and simplify, you'll come up with 0 equal to 0, which is true, and that shows that the given line is a tangent to the given rectangular hyperbola, and that's what they wanted. So now we shall go to hyperbola involving loci. So loci, we already covered it in this video, so there's nothing to write here. What we need to do is to go straight to the question. So question 1 says, came from UNEB 2015, paper 1, question 15, and says that tangents at points this P and Q. I think you realize that the variable can change. Previously we were using TT, now you can use P and Q. On a rectangular hyperbola, this intersect at R. Given that R lies on the curve this, show that the locus of the midpoint of PQ is given by this. So here we shall need a sketch. So let mx, m, which is capital X capital Y, be the midpoint of PQ. Therefore we shall come and draw our sketch, draw the axes and label them. Then draw your rectangular hyperbola. It must never touch the axes, because the axes are now the asymptotes. So we have a tangent at point P and also a tangent at point Q. They intersect at point R. We want the locus of the midpoint of PQ, and this is the locus they want. So you come and call the equation of the hyperbola, then differentiate it to come up with that. So the gradient function is dy dx, which is that. Now at this point P, x is this and y is this. Therefore, come and substitute for x and y, you'll come up with the gradient of the tangent. So now that I know the gradient of the tangent at point P and this x and this and the coordinates of point P, I can easily get the gradient. I can easily get the equation of the tangent at point P. So I come and say that using that point and the gradient, I can get the equation of the tangent from changing y over changing x equal to gradient cross multiply, open brackets, and simplify. That is equation 1, which is the equation of the tangent at point P. Then similarly, equation of the tangent at point Q will be given by, you replace P with Q. So this will be equation 1. That is equation 1, equation 2. Now equation 1 minus equation 2 gives you this. So when I subtract this minus this, gives you this. Then this minus this cancels, this minus this gives you that. So difference of two squares gives this. Therefore this and this cancels, you remain with that. Making y the subject gives you this expression. Now from equation 1 I have to get the corresponding value of x. So substitute for y and make x the subject. So when I make x the subject, I'll come and get the LCM there and simplify to get this value of x. Therefore the coordinates of R are these ones. Now I've got the coordinates of R. I'll come and say that but point R, they told us that lies on this curve. Therefore that means that this x coordinate, when you put it here and y put it here, it will be equal to c squared over 2. Simplify to get this equation 1. So we are getting the equation which has P relation between P and Q. So this would have been equation 3. then the midpoint P2 is given by this, the average of the x coordinate and average of the y coordinates. So when I simplify, I come up with that. Therefore x, this x is equal to this and this y is equal to this. So when x is equal to this, I'll come up with this, and when y is that, I'll come and substitute. Remember, I already know that cp plus 2 is equal to 2x, so the whole of this numerator will become 2x. Therefore, when I simplify, I come up with P2 as equal to x over y. Now from equation 1, actually it should be equation 3. So from this equation 3 here, we are now got the P2 and P plus 2. Remember, locus, like we said, under parabola and ellipse, locus, to get the locus, it means that we have to eliminate the variables. So this variable P and variable 2 have to be eliminated. The good thing, I've got P plus 2 here, and I also have P2, which I've already got. Now I'll come and substitute to come up with that. So simplifying gives me the locus which I want, and that's what they wanted. So that brings us to the end of this video. Thanks for watching, and bear in mind the next video will be on complex numbers. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video on complex numbers has been uploaded. And also, if you know any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we can all benefit as a family.